Alright, 5.3 is on what are called definite integrals. I sort of mentioned it when we got introduced to indefinite integrals. Definite integrals and the fundamental theorem of calculus. Okay, we're going to go straight to that theorem, because still this one's going to be mostly grinding out some techniques, not so much applications yet. Those will come in later sections. There's actually three sections that are devoted to different applications. Fundamental theorem of calculus. Related to integrals, if f of x, lowercase f, because we're going to use that capital F distinction. Lowercase f is a continuous function on the interval, and I'll be switching to interval notation when I don't want to keep writing a is less than x, less than or equal to x, less than or equal to b, but that's an interval from a to b. So in the future, I might just be using that as that interval. The area under the curve y is equal to f of x over a comma b is given by it's not a function. A, sometimes they define as a function. It's going to be defined as the integral of lowercase f, meaning we're going to be doing the antiderivative dx. But that'll give you a function only. Specifically, it'll give you your antiderivative, which we're going to use capital F. And usually we just have x and we put a plus c for an indefinite integral where we're looking for the antiderivative. But we will now be working with what are called limits of integration. And at the end, we'll be plugging those into your antiderivative, specifically in order. You're going to be doing the antiderivative at b, the upper bound, the right side boundary, minus the antiderivative at a. For any antiderivative f of x. And remember, there's an arbitrary constant of integration that you can make different antiderivatives from. They all are identical except for the constant term. They'll cancel out anyway. We'll talk about that when we get to an example. So we won't be dealing with that constant of integration. It'll just get canceled out from the subtraction here. Okay, let me draw a real rough sketch, because that's a definition given in the book, but I'm not 100% sure it's completely clear. You're going to have a function, f of x. You're going to have an interval from a to b. And it's the area under the curve trapped down to the x-axis. So it's going to be that area there that's given by capital A, which you can get by taking the antiderivative of this function and then plugging in that number and subtracting them in that order. I'm also going to mention another thing that doesn't really come up. Let me move this up. I haven't made my notes for future sections yet, but when I do, I think I'm going to incorporate an example that talks about this phenomena, but the homework that I saw did not, so anyway. It'll be that area that's given by this for f of x. Basically, under the curve, but down to the axis bounded by a and b. And it does mathematically work out to, and there's a reason it should, if you have a function that goes below. And if this is v over there, and that's a over there, doing this same process of doing the antiderivative, applying this fundamental theorem, will sort of give you the area, except that it'll treat this part of the graph that's below the axis as a negative area. Now in geometry we don't really consider area negatives, but for these purposes, yeah, we want to treat that as a negative because this is a profit. You're making money, accumulating money, and then that section will be you losing money, so it needs to be treated as a negative area. And again, it didn't come up on this section of homework, but I did want you to be aware it's not literally going to give you positive area like geometry. It'll treat above as positive area, below as negative area, so that computation will get you that area minus that area. Okay, we'll do some examples, but mainly it'll be doing more antiderivatives, getting more practice with that, and then learning to plug in these and then work it out and just talking about different things you got to worry about. Okay. Okay. We're going to do our first one, our simple one. Later on we're going to do trickier antiderivatives, but here it'll just be a pretty basic power rule. The book, first of all, I noticed the book uses parentheses if they have a polynomial or a function with multiple terms, and they'll cap it off with parentheses so you can see clearly what the function is, and then your integration notation. I'm not used to seeing that, to be honest with you. Usually they just write it all out, and you know what your integrand is, where it stops based on that dx. So I can put it, but really, other books won't put it. Anyway, that's what we called, this right here, which is not our problem yet, is what's called an indefinite integral, and there you would be looking for the antiderivative. You just need to do your power rule, x squared minus 3x, and adding the c, and that would be, it's your antiderivative with the arbitrary constant of integration, and that would be what you do for an indefinite integral. You're looking for just an antiderivative. Definite integral, which this is, and I'm not done writing it, has boundaries. That's the only difference. This is going to be from 2 to 5. And so those are x values on your x-axis. They don't ever write it, but I sometimes like to write it to remind myself. That's going to be a handy tool to avoid some mistakes in the future when we start doing substitution specifically. But anyway, how you handle this is you do the antiderivative, which I'm going to go through quickly. It's going to be x squared minus 3x. And this, I'm not going to work it out the way I'm going to do it in the future. I'm going to write more details, but this is our antiderivative, capital F of x, whereas this is our lowercase of x. Let's say we do throw in the plus c, which we're not going to in the future because it's going to cancel out, but let's do it for now. What I want to do for the fundamental theorem of calculus is take my boundaries and plug it into any antiderivative. So I'll be plugging 5 in, and I'll be plugging 2 in, and I'll be subtracting and being careful with that minus sign applying to every single term that I work out here. So I should have wrote this somewhere else. I'm going to write it somewhere else. Okay, so my antiderivative, yeah, I'll rewrite it. Bad. Okay, that's my antiderivative, and I want to basically do this. So I'm going to plug it. It's going to be 5 squared minus 3 times 5 plus some unknown constant, which I can throw in if I want for now. And I'm going to put big brackets around that because that's just my f of 5 right there. And I'm going to be subtracting f of 2. I'm going to plug in 2 everywhere. It's going to be 2 squared minus 3 times 2 plus the same arbitrary constant. Now, even though it's arbitrary, and you could assign it anything, but once you assign it, if you make that 7, it's a 7 there and it's a 7 there. You don't. It's not going to be different constant of integration. It's the same constant that you could arbitrarily pick, but when you distribute it, it's going to cancel out anyway. So let me work it out. With 25 minus 15 plus c, this minus sign distributes, so it's going to be minus 4 plus 6 and minus c. And right away, whatever constant we use in our antiderivative cancels. So in the future, we're just going to use 0, meaning we're just going to ignore it or not even write a c. So the c is going to be out for a definite integral with boundaries. My answer is going to be a numerical answer that I'm going to get by working this out. 10 plus 2, 12. 12? Yep. Okay. So constant is unnecessary, in case you are wondering later why I'm not using it, because it's just going to cancel out anyway. And that's it, but that's not the way they usually write it, so in the next example, or when we get to doing more of these, I'll talk about more the conventional notation on how you do it. I mean, you just, in theory, have to just do it and get your answer, and how you organize it is, in theory, up to the person, but there is kind of a standard way that I want you to see and get used to, so that your next professor, when he does it on the board, you won't say, what's he doing? You'll recognize the way of organizing this that is typical. Okay, before we get to that though, I just want to erase this, because I wrote too big. I want to give you a different type of problem. That really isn't a different type. They come up later in the homework, even though I'm going to do it now and get out of the way now. It's at the end of your homework. Find the area under the curve y is equal to 2x minus 3 on the interval 2 to 5. It's the same function that we just dealt with. It's the same interval that we just dealt with, meaning it's actually the same problem, just worded differently. It was mentioned in the fundamental theorem that definite integral gives you the area under the curve, and that's exactly what we're doing here. Sketching is not necessary. It can help you for trickier problems and help you to visualize it. But if you have an idea that it's just some basic function, 2x minus 3, so it's going to go through, my y-intercept will be -3, but it's only going to start from 2, so at 2 it's going to be at 1, it has a slope of 2, so at 5 it's going to be 1, 2, 3, 4. It's going to be 7. Okay, I don't need an accurate picture. I could just, to visualize, I could just draw a generic curve like that, and then just draw the region, and that'll help me do it. The computation, the accuracy of it's going to come from me doing an accurate antiderivative, so a lot of times you just got to have a rough idea of a function and see the boundaries, if that's helpful you to visualize it. You don't need to graph it accurately. Here I do want to, so I'm spending a little bit extra time doing something that will not be necessary in the future. Okay, so my function is linear. It's not always, it could be like a curvy exponential parabola, but this one is a linear function. Y is equal to mx plus b, slope 2, y-intercept will be -3, which it'll hit. It looks a little bit off, but yeah, it would in theory hit there. Okay, and I want the area under the curve between 2 and 5, so I'm on this area. And in the future, this might come up in a context that is not from an integral, it's not from a chapter on integration, so you have to remember, areas under curves you get to by doing integrals, specifically definite integrals. So you would set this up by setting up an integral of the function. There's no f of x, well, y, so I guess I can just throw it in. dx, your bounds of integration is from 2 to 5. And that'll give you the area. You don't even have to introduce the letter a if you don't want. You can just work that out, get an answer, and that's your area. And then here's where I'm going to do it more of the conventional way. You would find the antiderivative. I'm going to disregard the plus c knowing it's going to cancel. So when you do definite integrals, you tend to not worry about that, which means later on you forget when you are doing indefinite, and you got to remember so you don't get marked off a point. But here, I won't need it definitely. They write a vertical bar, and they write their boundaries here. 2 to 5, and that's saying we're going to take that function and plug in 5 and plug in 2 and subtract. So that's the notation they'll use. I will even go a step further and write x equals 5 and x equals 2. Again, that will be a tip that that could avoid confusion for a later thing that's going to happen. But for now, we're ready to plug in. Then they'll start plugging in. 5 squared minus 3 times 5. They'll plug in the 2. 2 squared minus 3 times 2. They will, if they're kind of careful and worry about mistakes, they will definitely make sure they know that that minus sign, f of a minus f of b, that minus sign applies to everything that I get when I plug in that lower bound of integration. From there, it's however you want to simplify basic arithmetic. Just, you know, I can do that all at first and subtract one number, or I can distribute like I did before. It's prone to mistakes. Especially when there's going to be fractions and you cannot avoid them in the future. You have to do common denominators. It can get ugly, but the main thing is that you understand the process. A minor mistake here is not going to hurt you too much the way I'm going to grade. 10 minus 4 plus 2, 12. And that gives you the area under the curve. With a with a linear function, oftentimes your region is like polygonal, like a polygon. Here it's a trapezoid. You could, in theory, use geometry, not for curves. If it was a curve, you pretty much have to use integration. That's why it's handy. But you can in theory verify this answer, and sometimes they do make you do it by doing geometry formulas. Now this is a trapezoid. You're not going to do this, but I just want to. You have the big B, which is the larger base. You have two parallel sides. This is your lowercase b oftentimes. Your height is straight up and down, and your area is 1/2 the sums of the bases times the height for a trapezoid. Again, I'm not making you do this. This is more for your edification that I could do it via trapezoids. It's sideways trapezoid. My two parallel sides are these two sides. That one is 7, because when you plug in 5 into the function, you get 7. This side is 1. You can barely see it, but so I have my two bases are 1 and 7. I'm going to do area is equal to 1/2 times the sum of the two bases, 1 plus 7, times the height. The height is straight up and down from parallel side to parallel side. That's this distance here. Again, it's sideways, so that height is that 3 right there. 5 minus 2 is 3. So that's 1/2 times 8 times 3 is going to be 12. So using the area of a trapezoid formula could work here. It won't work for other curved functions, but it worked here, and it confirmed that that antiderivative gave us the area under that trapezoid. Okay, but anyway, we're not doing geometry, and you're not expected to remember that, although it'd be good. We're just going to be doing things this way. If you want to do areas and curves, for the rest of the problems, I'm just going to give you a definite integral to do, get some practice with that, practice techniques, and talk about how substitution is going to make it a little more complicated, and we'll have to handle that. But from here, we're just going to grind out a bunch of these, getting you some practice with that, and your homework's going to be similar. Okay, just grinding out some examples. Evaluate the following definite integrals, which means you're just working them out to a numerical answer. All right, first one. We're going to start basic and work our way up. The level of difficulty goes up purely based on you having to do substitution. We're going to do one of those and talk about it. And the substitution gets trickier and trickier. We're going to have exponentials and logarithms pop in and deal with simplifying those expressions. But this one's straightforward. Okay. You want to do the antiderivative and then plug in 4 and 2. So you're ready. Sometimes you have to do some work, simplify it, expand it, do substitution. We're going to talk about, like I said, But here, if you're ready to go, you can do the antiderivative. I'm going to, prior to this, I would have been doing 3, and I would do the power rule on the 2, bump it up, do that, and then cancel the next step. I'm going to start skipping a little bit of steps, so be aware of that. So for instance, this is going to simplify to x cubed. You can mentally check that by taking the derivative of that and seeing if you get that term. You can do the check mentally, term by term, as you go along. Answer to that's going to be x. No need for the plus c because I am using -2 and 4 as boundaries or limits of integration, and I'm just going to plug in to get a numerical answer. 4 cubed minus 4 minus -2 cubed, I can watch that, that's still going to be negative, minus a -2. Lots of negatives in this one that I have to be careful about. I'll work out inside of here. Well, I'll work it out term by term, but eventually I'm going to distribute the minus sign and just add 4 terms. But there's many options on how you handle it as long as you're careful and keep it organized. That's going to be a -8, that's going to be a +2, both those being still inside that. +8 minus 2. Alright, I'm ready to go. It's going to be 66. And that's the numerical answer. That's a value of that definite integral, and it would be the area of the curve of that function between -2 and 4, and 66 is correct. I'm just going to confirm. It is, like I said, it's prone to like an arithmetic error, which is not a big deal in my opinion, as long as you get the gist of how you go about it. Okay, I'm going to have to spend a little time on this one because this one's going to involve substitution. Now, it doesn't require substitution. There's going to be ones later on where you're going to have to use substitution, but I'll be honest about this one. In theory, you could just expand it. It is a polynomial. It would be a little bit messy, but not too bad. It's doable. You'd have to cube this x cubed minus 1 cubed, multiply 3 of those together, FOIL it all out, distribute this 12x squared, and get a polynomial with, I think it's going to be, it would be like 4 terms. Pretty big powers. And then do the antiderivative via the power rule like we did over there, and then plug in the value. So it could be done by expansion. In theory, you wouldn't need to use substitution for this. But I am using this one to illustrate what happens when you try to apply substitution to a definite integral. So I'm going to be using substitution, meaning this piece here to the cube, noting it's a cube. And when I do set u to, if I set, I'm anticipating what's happening. If I set u to be that, my d will cover an x squared because I have 1 power down. The 12, I'll just worry about that afterwards. But that x squared there, it's going to come out nicely with the dx when I do my du. Let me turn off the sound on my Zoom meeting. Okay, and again, it's trial and error, so maybe this doesn't work, but it will, because I've designed it to work out via substitution. My du will therefore be 3x squared dx. I'm not gonna try and break up that 12 into 4 and 3. Instead, I'm just gonna isolate the x squared dx part, and so x squared dx will become 1/3 du, and then now I'm gonna put it all together. Going back to my integral. 1, 2, let's see. Well, yeah. I'm going to pull the 12 out. So 12 is coming out. I have my x cubed minus 1, which is u cubed. What's left is that x squared dx. That's going to be 1/3 du. And now I'm going to note a very important thing that's related to substitution. Well, I'm going to backtrack a little bit. Let me pretend I'm going to just power through. The 1/3 I'm going to pull out. I'd be doing the power. Now, I still haven't done the antiderivative. I just did substitution, got an integral. That's a much simpler version of it. That's what substitution does. I'll be doing the power rule on that. Cancel that 4, and I will get a u to the 4th. If this were if this were an indefinite integral, I would just want my final antiderivative with the constant of integration as a function of x. So I would go ahead and just rewrite that as that. And it'd be done if it was an indefinite integral. But I have a definite integral, I gotta plug in values. But here's where I'm gonna erase and I've gotta organize this, because there's two different ways you could approach it. So that's the idea. I'm gonna be doing that antiderivative. Well, yeah. But let me hold off, because what I have to worry about is the point at which I'm gonna be plugging in my limits of integration. These values here were x values to be plugged in for x. It's going from the interval from x equals 1 to x equals 2 of this function in x. We introduced u, but as of now, and I'm going to highlight it in red, that's like a thing to note and an important thing you got to be on the lookout for. That's an x equals 1 and that's an x equals 2. I'm going to do what I did earlier. I'm going to move that 1/3 out, cancel with that. And at this stage, I'll write that. Okay. I'm going to take the antiderivative. So I'm ready to do the antiderivative. I'll do my limits of integration afterwards. It's going to be u to the 4th over 4 when I use the power rule. I'm not going to bother with the plus c because I know it's going to be a definite integral and I'm going to plug in values. And again, I'm going to note. And they don't usually do this x equals x equals. They just have you mentally be aware that the 1 and the 2 are x values. I will be writing explicitly for notes. I tend to do that on my actual own personal work as well because I'll forget and it'll mess me up. But anyway. The issue is you do not want to accidentally, well, if they just write the 1 and the 2, it is a somewhat common mistake for people to just throw in the 2 into there and raise to the 4th power, throw in the 1, subtract it, and get an answer that is wrong because these are x values. And so I need to plug them in for x, which means that I need to rewrite this my antiderivative in terms of x. So I have to go back and substitute in place of u x cubed minus 1, and I'm still evaluating a definite integral. I'm running out of space, but and now at that stage I've had the antiderivative expressed in oh shit, I forgot the 4th power. And now I have my antiderivative expressed in terms of x, and now I can plug in those x values. That's my boundaries of integration. I'm going to do that quickly. It's just algebra. It's going to be 2 cubed. I'm skipping a few steps because I'm running out of room, but you get the idea. 2 cubed minus 1 is going to be, well, 8 minus 1, which would be 7 to the 4th. It's going to be a big number for sure. Minus 1 in f for x is going to be 1 cubed minus 1, which would be a nice clean 0. So all I got to do is 7 to the 4th power, whatever that is. Work out the algebra more slowly and carefully if you need to, but I'm out of room and I'm going to redo this problem in a different way to illustrate the two different ways you can approach an integral, a definite integral, where you're going to apply substitution. Okay, let's see. And different structures will just teach one way and you'll learn that way and then probably just go with it the rest of your life. I will at least show you both ways. I don't even know which way I'm going to be doing in the future. In the future, I'm only going to do one way, and I'm not even sure which way I'm going to go with, to be honest with you at this stage. Okay, so let me start from the beginning, sort of the beginning. Nothing's going to change. We are still applying we're still applying substitution. It's the same integral over there, so I'm just doing the substitution here. Okay, I'm going to pull out the 12. Sorry, let me redo this. I'm just recopying it down, but I'm leaving space for something that's relevant to the right of this. I'm at this stage. As of now, I'm doing the same thing. I'm going to pull out the 12, to rewrite my integrand as u cubed. The x squared dx becomes 1/3 du. And here's where I can do things differently, and some professors will do it differently. Those x values, I can convert those to u values. How do I do that? I basically use this relationship between u and x. So right here, I have two boundaries. Doesn't matter which one I'm going to do, but I'll do it in the way it appears on the board. X equals 2. When x is 2, u is equal to 2 cubed minus 1, which is equal to 7. So my upper bound is x equals 2, which translates based on this relationship as u is equal to 7. So I can use a u bound now. I'm going to do my other bound, my x equals 1. My lower bound, when x is 1, u is equal to 1 cubed minus 1. When I plug in that x value into here and I get a u, the equivalent u value, I get 0. And so I can use, when x is 1, u is 0, and I can use u is equal to 0 as my lower bound. Alright, and I'm going to finish it up now because I'm going to pull the 1/3 out, it becomes a 4. That's just rewriting my integral. I have not done the antiderivative yet. I will do it in the next step because I'm ready to go. Just a power rule, the basic power rule. It's going to be u to the 4th over 4, which will cancel that 4. I'm going to skip that step. And I'm going to note now that I don't need to, if I do it this way, where I've converted everything to u, including the boundaries, I do not need to go back to x. I'm done with x. I want a numerical answer, specifically 2401, and I can just use these u values right into here. So it's going to be 7 to the 4th minus 0 to the 4th. And when I work that out, I get the same answer. It's actually the same things you've done, except that this plugging in the 2 into x and getting 2 cubed minus 1 is equal to 7, and the 1 here, I did it up here and replaced my bounds of integration, my limits of integration with u's, but that same computation I had done here at the later stage by plugging in late. So you're doing the same thing, just in different orders. But you can't confuse the two. You need to keep track of what variable your limits of integration is. Either convert them everything to u, convert your bounds as well, and then never have to go back to x ever, or leave it as x and just make sure you are plugging them into the antiderivative written in terms of x. So that's the distinction between the two methods. And again, a typical professor only teaches one way, and you kind of just learn that and go with it. I'll think about what I want to do in the future. I'm probably going to switch my bounds. I feel like that's the most common thing that I see professors and books do. That is sometimes useful for certain reasons, I think, but I can't really explain it now. I'm going to be doing this for the remainder of the problems, and they will involve substitution. So I'm going to start just converting my bounds along with my variables of integration. Okay. Okay, let's see. 0 to 3, x squared to x squared plus 16 dx. Okay, you can't really work with any kind of expression or function in a radical without substitution, so probably substitution. Let's see. Usually if you have a radical anywhere and you have an expression in there, and it's not working out nicely or it's not a nice one, you might want to try at least setting your u to be radicand. Hopefully it works out. Hopefully the puzzle pieces fit together. When you do your du, that's always an important thing, to convert your dx to du. It's going to be the derivative of this 2x dx. And I have an extra 2 there, but that's not a big deal. I can move it around and get 1/2 du is equal to x dx, covering that x and the dx, which means when I rewrite this, it'll be, where am I at? Sorry, square root of u, my whole radicand is u, the x dx becomes 1/2 du. When people write this, sometimes they start moving things around already, but I like to see that's radical, the dx converted to a 1/2 du, the x dx converted to a 1/2 du. Bounds, let me change my bounds. Okay, so over here, when x is equal to 3, plug in 3 into there, u is equal to 3 squared plus 16, which is 25. 25 is my new u bound. When x is equal to 0, u is equal to 0 squared plus 16, which is 16, so my lower bound is 16. Okay, so, and if I want to remind myself that I'm good to just go and plug these in for you, I can add that in if I want, and I do oftentimes want to do that for my own personal strategy to avoid errors. Okay, taking this antiderivative, I gotta rewrite it as u to 1/2. That's not doing the antiderivative, that's rewriting a radical as a power. I'm ready to work with that now. It's gonna be u to the 3/2. Gonna bump that up by 1. I've got to divide by that power 3/2. At this stage, I'm gonna start just noting that that's gonna be the reciprocal of that. If it's a fraction, if it's divided by a fraction, same thing as multiplied by the reciprocal. I will not be going back to x because I will just plug in these u values right into there. I just got to be able to handle the 3/2 power. Okay, coming up here, my coefficients out there simplify to 1/3, and now I'm trying to do 25 to the 3/2 minus 16 to the 3/2. And the 1/3 applies to both of them, so I can put a 1/3 there and a 1/3 there, or I can just treat that 1/3 as being multiplied by the whole thing. Either way is good. Just make sure you know that that coefficient of 1/3 does apply to, that's part of your antiderivative. Here I'm essentially factoring it out. Okay, let's talk about this, make sure we can do that, because that's a thing from previous classes, but I know it's going to come up and not everybody remembers it. That's going to be the half. You can think of it as a radical, which is a square root. So these are going to be nice numbers, or nice, well, somewhat nice. And the 3 on top means you're going to be cubing it. Because you're thinking of that 25 to the 3/2 is you're splitting it up into ways you can handle, and what you can handle is to treat that as 25 to the 1/2 all raised to the 3rd. That's equivalent to a 1/2 times 3 or 3/2 power. So we're treating it like that. And rewriting that half power as a radical, so we can think about it in terms of what's the square root of 25, and it's 5, and I want to cube that. So it'll be 125 for that piece only. Keep in mind that's part of a larger thing, but here I'm doing the same thing. It's the same power for 16. Square root of that, but cubed. That'll be 4 cubed, and the 1/3 again multiplied by the entire thing, or both antiderivatives. Alright, 125 minus 64, whatever that is, you will need a calculator for some of these, because the numbers, I can't help but make the numbers go large, and I'm not going to be avoiding fractions, and I'm using this section also to make sure you can handle fractions. Okay, it gives me 61 times the 1/3 is over 3. Does 3 go into 61? Nope, so that is reduced. That's your answer right there. 61/3. Okay, and here I changed my bounds to u, but I did make a note of it, so to remind myself. Okay, next problem. I got 4 more. We have logarithms and exponentials in a bit. This next one, kind of forgot to do an example that has this particular thing come up, so I'm going to do it here. And what I mean is just common phenomena that occurs with substitution. x plus 1 squared over root of x. Okay, and again, this is one that you could, in theory, expand that. Your bottom is a monomial. You will be able to, let me just mention how you could approach it. I could FOIL that out. It'd be 9x plus 6 squared of x plus 1. When you FOIL that top out, it's over a single power of x, so then you can break it up and reduce each of these to a single power of x. It'd be totally doable that way. I'm not going to do that way because I do want to talk about substitution that involves a square root of x. So that's fine if you do it that way. But there's going to be another problem that comes up where you will want to set u, do u substitution, and set u to be an expression that involves the square root of x. And I'm going to do it slowly. Okay, I got to do my du and see if it works out. Notice that piece will be the top. It'll be u squared at top. I have this extra. So the extra thing that's not accounted for right away is that. But it is going to fit perfectly. So I want to make sure we can understand how this works. When I take the derivative of this, that's going to be, I want to work it on this side. The derivative of the square root of x, which we've done in the past, but I'm going to come back to it, is 1 over 2 square root of x. The 1 is 0, so I get that. So my du will have a square root of x in the bottom. It will account for that square root of x in the bottom. Let me just remind you on the side here. I'll just say recall as a side thing, because I don't want to do the work in there. It's just going to clutter that up. But the derivative of just the square root of x piece is the same as the derivative of x to the 1/2, which requires it. This is a derivative, so you're bringing the power down. I'm going to do the power rule, differentiate via the power rule. Make sure you don't confuse it with doing the antiderivative via the power rule. They're two separate directions. Bring the half down, subtract 1 from that, gives me negative 1/2. That negative 1/2 power is a radical on the bottom, a square root on the bottom, so that becomes that. The 1 over 2 times that means there's a 2 on the bottom. So the derivative of the square root of x is that. And it's common enough, it comes up enough where you might want to kind of just know that and not have to go through the steps of rewriting as a power, bringing the power down, rewriting it back as an expression with a radical. So that's what I did here, right there. Derivative of that, I'm trying to do du, bam, right there. 3 comes down, that becomes 0, and I do have that. It's 3/2 times 1 over root x dx is du. I'm going to move the constant over as usual, using the reciprocal of it, but leave all the x's there, and note that that is perfect, because that right there accounts for that. So that's going to be right there, and that I circled in blue is 2/3 du. The numerator there is just u squared, and so substitution does work, even though it was not necessary. So let me write it out. I got u squared up top. That times that is all of that, which is just times 2/3 du. And my boundaries, which I did not do, so let me go do that here. I'm on the side here, sorry. When these are x values, when x is 4, I'm not going to write out all the steps, but I'm going to go with u is, I'm just going to do it mentally. When x is 4, it's going to be square root of 4 is 2, 3 times 2 is 6, 7. U will be 7. When x is 1, square root of 1 is 1, 3 times 1 is 3, plus 1, 4. U will be 4. Okay, a lot of times I pull that out and then I rewrite it and then I do the power rule. I'm going to just do the power. I'm pulling it out and doing the power rule at the same time. The 2/3 is going to come out. I'm going to bump that power up by 1. I'm going to divide by 3. And then I have to plug in 7 and 4. Okay. I don't need this anymore. I got 2/9 times times 7 cubed, and then 2 9 times 4 cubed. Minus 2/3 times 4. 2 9 times 4 cubed. I'm just going to write it out like this. So it's going to be 7 cubed minus 4 cubed. Alright, let's see what we got. 7 cubed. It's 343. 4 cubed, I know it's 64. Says it's a whole number, and is that going to come out to a whole number? Hey, it does. Okay, so 9 does go into that. And then, so that's times 2. Okay, just didn't look like it was going to come out to a whole number. 62. Okay, I designed it somewhat nice. Alright, that is, note that trick, or note what happens when you have to set a u to have a radical x. You'll end up with a d that has a radical x on the bottom, and that may be what you want. It is what we wanted there. So that radical x on the bottom, which makes it look complicated, makes it the pieces actually fit, because that's going to be part of your du. So keep that in mind. It's going to come up on one of the problems I know for sure, and it's a common thing that occurs in future math classes. And again, that will eventually have a meaning in some applications. The 62 will represent something. That's a later section. I'm just going to make sure we can do this proficiently before we start trying to think about some application in addition to the steps. Next one. Okay. On B, right, there's sometimes other ways to do it. Well, I've mentioned options on some of them. The last one had several options. I mean, this one, be aware, last section, it was all substitution, so you pretty much knew you had to do it. Now it's going to start to mix in together where you might use substitution, you might use other techniques when you learn them. You might even not even have to do any special technique other than what we did in the very beginning, which is note that when you have a single power of x in the bottom and a polynomial on the top, you can break it up. I can rewrite this as 4x squared over x plus 1 over x, and it becomes just powers of x. Again, I could have done that the last time, but I wanted to illustrate that radical x thing. Simplifying this is 4x, 1 over x. Do you want to write this as x to the -1? Do we? Because usually when it's a power of x on the bottom, you write it as just a regular power of x with a negative exponent, and you do the power rule in all of these. Except for that's the one that doesn't involve the power rule. That's the one that is logarithm. So I'll leave it as 1 over x. It doesn't matter as long as you recognize that that's not going to be a power rule to be applied. That's going to be a natural logarithm as your antiderivative. Okay. So I'm not doing substitution. I'm going to leave these as x values. I'm just taking a straight antiderivative. Power rule on that's going to be 2x squared. That's not a power rule. That is an ln of the absolute value of x. And we're going to be plugging in positive values anyway, so that's another situation where that doesn't matter. Alright. And I just want you to know for your exact answer, a lot of times you have expressions involving logarithm or exponential e. You have answers that will have e in them. Here I'm going to plug in, and I'm going to be 6 in all of these. So 2 times 6 squared plus ln of 6. No need for the absolute value since x is positive anyway. Let me change that to brackets so it's easier to read the nesting. Minus 2 plugged into the entire antiderivative, which is both places. So 2 times 2 squared plus ln of 2. Okay, there's numerical factors that I can just combine. I'll write it out. That's going to be 72. ln of 6 is not a nice thing. You can do it on your calculator and get a decimal approximation. It's an irrational number. It is specifically, let me just do it to me. I'd just like to make sure I understand that. It is the value that is approximately 1.79-ish. If you need a decimal approximation, you go ahead and use that decimal approximation and do the same thing for the 2. But if you want an exact answer, you're not doing that. You're going to leave it to ln 6. Minus 8, and that minus applies, so it's going to be minus ln of 2. You want to combine what you can, generally, so definitely the 72 and the 8. 72 minus 8 is 64. Okay. 64, and I got a plus ln of 6, and I got minus ln of 2. And you're sort of good. I'll accept that. And I wanted to, illustrate that a lot of times you will have expressions in your answers that you can't simplify, so exact answers will just involve natural logarithms of certain values. I also want to mention, when you do have a situation where logarithms are in your answer, it's a very common thing to want to go to the back of the book and look at your odd answers and verify you did it correctly and see something that looks completely different. So let's say you look in the back and you see 64 minus ln of 3. And it's very common for somebody to work it out and look at an answer and just think, oh my god, what happened? What did I do wrong? Look through their work, not find a mistake, and just wonder, how the hell did they get this answer? With logarithms, a lot of times there's so many ways to rewrite it with the rules for combining them and canceling them, that I can use the rules for logarithms, and oftentimes they do. They combine it to a single logarithm via the rules. So that's 6 divided by 2. That's a quotient rule for logarithms. And then when you simplify that, you actually just get ln of 3. And why do I have... I'm going to check this. I'm saying it's this. But my answer sheet over there says this. So if this was in the back of the book, I'm saying it's wrong. And if... yeah, let me double check this. Did I do this right? Yeah, so I think it's plus 3. Okay. I'll double check it though. I'm going to pause it because I've got to make sure that the answer is correct, and I'll come back and verify. Okay, so yes, this is the correct answer that probably would appear in the back of a textbook. This is, I want to say I would accept it. It may not be considered simplified if they have some convention of you need to combine your logarithms when possible. It's definitely possible. But I just wanted you to be aware that logarithms answers can look so different in different forms. Just be conscious of that. Next one, we're going to have from integral from 1 to e to the 5th power of ln of x over x dx. Don't panic. Don't look at those limits of integration and think, oh my god, how are we going to handle that? Usually when you see something really weird in your limits of integration, it's because it'll work out nicely. And this will, because our antiderivative will involve natural logarithm, and when we plug that in via the nature of exponential logarithms that they're inverse functions, they'll cancel, and that phi is going to come out probably. It is, but yeah, so don't worry. But for now, let's just work out the problem. You have 2 pieces, there's no nice antiderivative of that, you can't break it up like we did the other things, so probably substitution. If you recall, we've done a couple of these where you never want to set u to be x, because again, that just you'll just have the exact same integral, but in terms of u, and even if you convert your bounds, it's still going to be the exact same thing, but in u, so it literally gets you the same integral with just a different letter involved. So again, u is equal to x will not do anything at all. Your only other piece is u is equal to ln of x, but be aware, and if you did enough of these with a natural logarithm of substitution, you know that your du will cover that x in the bottom. Perfect. So this is good. I'm going to have just u, du. That's it, right? Because that's your u to the 1st power just by itself. The 1 over x dx gets covered by du, and that's your integral in terms of u. My boundaries are not in u, and as I said, I decided I'm going to do converting bounds consistently from here on out. Okay, so what's going on with this? These are x values. You don't have to write this every time. When x is e to the 5th, u is equal to, and I will spend a little time doing this, u is equal to ln of x. And now you have to recognize that that does simplify. Natural logarithm of e. Natural logarithm is log base e, and if it's that same base and that base to some power, your logarithm is giving you a power. So that's u is equal to 5. So again, that fact that you have such a weird boundary actually works out because it involves natural logarithms. The other one, when x is 1, u is equal to, I forgot to write u is equal to. U is equal to ln of 1. That was a common one that I said you gotta kind of recognize that, because if you leave it in your answer, they consider that not simplified. Now, any logarithm of 1 is 0, including natural logarithms. So ln of 1, always 0. So u is 0. From there, it's not even any kind of, it's not even a weird one. It's just a straight, oops, I'm doing antiderivative. It's just a straight power rule. What am I writing? Some of these texts begin to bother me. Okay. U squared over 2, and I'm going to evaluate it from u is equal to 0 to u is equal to 5. Alright, plugging it in. 5 squared over 2 minus 0 squared over 2, and I get 25 over 2, and I'm done. Okay, so that one just illustrates, reminds you of substitution involving a logarithm, that one over x, that x on the bottom is good, and also to not to panic when there's an exponential e to some power, and your antiderivative involves logarithms, because it's usually designed to come out clean. I got one more. You're good with that. Okay. In a similar vein, here I'm going to have e to the 1 minus x dx from 4 to ln of 2. And again, don't worry about the weird boundaries. It's usually designed because it'll cancel out with the exponential or the inverse functions. There is no antiderivative for e to some function. You have to use substitution to handle that. So usually in that situation, we've done it before, you set u to be that exponent. And if there's extra stuff, powers of x on the outside, hopefully that gets accounted for the du. There isn't. But fortunately, we don't get a power of x when we do our du is equal to whatever dx. We just get the coefficient -1. That's relevant. We do need to worry about that and work this out slowly via substitution. I'm going to move the negative over, just like I did with any constant at that stage. Like if I had a 2 there, I would divide it. And so same thing, even if it's a -1, I'm going to move it over so that I get dx is equal to negative du. Let me change my bounds. When x is ln of 2, u is equal to 1 minus ln of 2. Still looks ugly, didn't clean up at that stage, but we'll see what happens. When x is equal to 4, u is equal to 1 minus 4, which is -3. So those are my boundaries. So I've got e to the u. Don't forget dx, you have to convert to du, and it's equal to negative du, so you will get a negative coming out of this. I've got u is equal to -3. And I've got u is equal to 1 minus ln of 2. Okay. That's just a -1 coming out. The antiderivative e to the u is e to the u. So that's my antiderivative there. And all I got to do is evaluate that at -3 and 1 minus ln of 2. And that's going to go into an exponential. And the exponentials and logarithms cancel, but a little bit trickier, and I got to be a little more careful this time. And I got to worry about that negative. Make sure you're doing it in the correct order. Upper bound first. Negative e to the 1 minus ln of 2. Then I'm going to subtract a negative e to the lower bound. So I'll be doing minus of that negative antiderivative. So it'll be e to the -3. I need some space for that natural logarithm piece to do it carefully. So let me go this way. Let me just clean this up first. 1 minus ln of 2, and it's going to be plus e to the -3. Okay, there's no rule for combining the same base but with a sum, but I do definitely want to simplify this, so we're going to talk about that. Yeah. To be able to simplify that logarithm, you need a clean e to the ln of something will equal that something. And that 1 minus is creating a problem for us in that sense. We can't just cancel those out because you got 1 minus that. The way to handle that is to break it up as a product. It's going to be e to the 1 times e to the negative ln of 2, because the rule there says if you have a sum of exponents, they come from a product of exponential expressions with the same base. So we're going in reverse. This is what's called the product rule, where you multiply two exponential expressions with the same base, different powers. You can just combine those powers by adding. This is going in reverse. Two numbers that are added, I can break it apart, but it's a product of those. Yeah, I don't know if I should. Okay. And that negative is still an issue. I feel like I maybe should have taken care of that right away. Anyway, that's just. Here's what I'm going to do. There's different ways to handle it, so I'm thinking about what the best way is and what the most clearest way is. I could rewrite that like this. Just break up that coefficient, -1, put it on the outside, and then I have that clean ELN, and it'll come out to a 2 to the -1. I was thinking I could also just move these negative powers in the bottom. I got a couple of them, so I'm going to handle it now. So any negative exponent, I'm going to move to the bottom. This is a negative on the outside. That's e to the 1 that's going to stay on top. And I'm going to move that whole thing with a negative ln of 2 exponent. Move it to the bottom, and it changes to ln of 2. To be clear, that's just, if you're confused about that, just know what I'm doing here. E to the -3 would be rewritten as 1 over e to the 3rd. I'm doing literally the same thing with a not so nice exponent, but same idea. A negative exponent can be written by moving to the bottom and changing it to a positive. Okay, all of this is just trying to simplify this to an answer that satisfies my professor. E to the 1 is just e. E to the ln of 2 via that is 2, just so that comes out as a clean 2. I mentioned that was going to happen, but it took a while to get there. And this is just a 1 over e cubed. And that's one form of our answer. We could, if you look in the back, they may have chosen to combine with a common denominator. You would need 2 there and e cubed there to get a common denominator of 2e cubed. And what you would have is negative e to the 4th plus 2. That would work as well, combining it into a single expression with a common denominator, or not. That's fine as well. A lot of times they don't want the negative exponents, and definitely wouldn't consider this simplified. So if you see e and ln, they want you to somehow resolve that. And again, it wasn't as clean. We had to like break it apart and do a bunch of things to get it down to the stage where you had just e to the ln of 2. Came out as a 2. Okay, that's a lot of different substitution problems. Folded in with the new context, or the new concept of plugging in the limits of integration and getting the numerical answer. That again, this is just some number. You plug it into your calculator and get a decimal approximation if you needed it. But mostly we're just learning the techniques here. Applications are to come in later sections. We've only got a few. We'll see. Okay, anyway, that's it for 5.3. See if you can tackle the homework. Just grind it out.